Welcome to the Deep Dive. We're here to cut through the noise, untangle complex ideas, and really deliver the essential insights straight to you. Today, we're diving into something that, oh, it sounds a bit textbooky maybe, gas mixtures. But trust me, this has massive implications for industrial systems, for understanding energy. It's everywhere. We've got a stack of expert sources, a really detailed textbook, actually, to help us unpack how different gases, behave when they come together. You'll discover the rules, yes, but also some pretty surprising things about energy, and even why a river flowing into the ocean, why that's this huge untapped power source. That's kind of wild.
It really is fascinating because these seemingly simple concepts, like just mixing stuff together, they unlock these profound thermodynamic principles. And these aren't just abstract ideas. They quietly influence, well, pretty much everything. The air you're breathing right now, the efficiency of chemical processes, it's all connected.
Okay, so let's unpack this then. We often talk about pure substances, right?
Right.
One gas at a time. Why do we suddenly care so much about mixtures? What actually changes when you mix things up?
Well, you see, most real-world applications, thermodynamically speaking, they don't involve just one pure substance. Think about air itself.
Right, nitrogen, oxygen, other stuff.
Exactly. And if we had to create, like, endless property tables for every single possible combination of gases, it'd be impossible. Just not practical. So understanding mixtures lets us predict their behavior, their properties, without having to reinvent the wheel every single time. It's about finding the general rules.
That makes a lot of sense. Okay, so if we have a mix, how do we even start describing what's in it? Is it by weight or something else?
Good question. There are basically two main ways. You can use what's called molar analysis. That focuses on the number of moles of each component, leads to the mole fraction, or you can use gravimetric analysis, which, as the name suggests, specifies the mass of each component, gives you the mass fraction, and it's pretty intuitive, really. The total mass of a mixture, it's just the sum of the masses of all the parts, same for the total number of moles, and whether you're using mass fractions or mole fractions, they always add up to 1 for the whole mixture.
Ah, okay, so it's kind of like baking, right? You can measure your flour and sugar by weight, grams
Yeah.
or whatever, or by volume, like cups. Either way, you get the full recipe.
Precisely, that's a great analogy. And from these compositions, we can also define things like an apparent molar mass, sort of an average molar mass for the whole mixture, and an overall gas constant for the mix. These are really useful because they let us treat the mixture, for certain calculations anyway, as if it were just a single uniform substance. Simplifies things quite a bit in engineering. Like if you have hydrogen and nitrogen mixed, we can calculate a single average molar mass. Helps us understand its overall density, how it behaves compared to just pure hydrogen or pure nitrogen.
Okay, now here's where it gets really interesting for, practical stuff.
Yeah.
When does a gas mixture act ideally? Nice and predictable.
Yeah.
And when does it start getting complicated? When does it go off script?
Right. So an ideal gas, that's really a theoretical concept. It assumes the molecules are so far apart they don't interact at all. And this is a pretty good approximation when density is low. So low pressure or high temperature generally. And the crucial part here, a non-reacting mixture of ideal gases, it also behaves as an ideal gas.
Like air, usually.
Exactly like air.
Uh-huh.
We often treat air as ideal because nitrogen and oxygen, the main components, they act pretty ideally under normal conditions. Low pressure, room temp, that sort of thing. Now, for predicting the PVT behavior, pressure, volume, temperature of mixtures, we generally lean on two main models. First, there's Dalton's law of additive pressures. This law basically says the total pressure of the mixture is just the sum of the pressures each gas would exert if it was completely alone in that same container at the same temperature and volume. And the second one is Amagat's law of additive volume. Similar idea, but for volume. It states the total volume of the mixture is the sum of the volumes each gas would occupy if it existed alone, but this time at the mixture's temperature and pressure.
Okay, hold on. So, Dalton's law. If I have a sealed tank of air, the total pressure is literally the pressure the nitrogen would create if it was the only gas in there, plus the pressure the oxygen would create if it was alone. They just add up like that.
Yes, precisely. For an ideal gas mixture, that's exactly how it works. Simple addition. And for these ideal gases, it turns out the ratio of a component's pressure to the total pressure, we call that its pressure fraction, is exactly the same as its volume fraction, and also exactly the same as its mole fraction.
So the mole fraction tells you a lot.
It really does. It tells you its contribution to pressure to volume.
Yeah.
Very useful for ideal mixtures.
But what if it's not ideal? You mentioned high pressures, low temperatures.
Yeah.
Getting industrial stuff, right? Where gases get squeezed or chilled. Does the math still work? Or do things get messy?
That's exactly when things get messy. Or well, more involved. And that's where the real engineering challenges pop up. For real gases, where molecules are close enough to interact, those simple laws are just approximations. We need better tools. One common approach is using the compressibility factor, Z. We can find an overall Z for the mixture, Z, by taking a weighted average of the individual Z factors for each component, weighted by their mole fractions. And interestingly, in these non-ideal cases, Amagat's law often gives more accurate results for the mixture properties than Dalton's law.
Really? Why is that?
Well, it seems Amagat's approach, by using the mixture pressure, implicitly does a slightly better job accounting for those intermolecular forces. Dalton's tends to underpredict the pressure when gases are dense. Another really useful method is K's rule. This one's clever. It treats the mixture as if it were a pseudo-pure substance. You calculate these pseudo-critical properties, pressure and temperature for the mixture, based on a weighted average of the critical properties of the components.
Pseudo-critical, so like fake critical points.
Sort of, yeah. It lets you use the standard compressibility charts, but with these adjusted values for the mixture. And K's rule is pretty robust, usually gets you within about 10% accuracy, which is often good enough for engineering work.
Okay, let's see the impact. Because this sounds like it could make a big difference. There's an example, right? A tank with nitrogen and CO2 at high pressure.
Yes, exactly. Let's say 2 kilomoles of N2, 6 of CO2 at 300 Kelvin and 15 megapascals. That's high pressure.
Right.
If you just assume it's an ideal gas mixture, you calculate the tank volume to be about 1.33 cubic meters.
Okay.
But if you use K's rule, you get 0.652 cubic meters.
Whoa, wait. Less than half.
Less than half. And if you use Amagat's law with the compressibility factors, it's even a bit smaller, 0.638. Dalton's, using Z factors, gives about 0.648.
So K's, Amagat's, Dalton's for real gases. They're all clustered down there around 0.6 something.
Exactly. They're close to each other.
Right.
But they are drastically different from that ideal gas value of 1.33. And this is the critical point. Assuming ideal gas behavior at high pressures can lead to huge errors. Unacceptable errors in many cases.
That really makes you wonder. If the error is that big for volume, are we making similar mistakes, maybe without realizing it, when we calculate other things? Energy, heat transfer.
That's the right question to ask. So let's talk about other properties. What about things like energy or enthalpy or heat capacity?
Yeah, how do those work for mixtures?
Okay, so for extensive properties, remember, those depend on the amount of stuff you have, like total internal energy, total enthalpy H, total entropy S.
Right, the total amount.
For those, it's generally additive. The total energy of the mixture is just the sum of the energies of each component. Simple enough. But for intensive properties, things that don't depend on the amount, like specific internal energy, specific enthalpy H, specific heat, CV or CP.
Per kilogram or per mole.
Exactly. For those, we use a weighted average, based on either the mass fractions or the mole fractions of the component. So equals the sum of mass fraction times weight or the sum of molar fraction times weight if using molar specific energy. These relations are actually exact for ideal gas mixtures, and they're usually pretty good approximations for real gas mixtures too. For ideal gases specifically, we rely on the Gibbs-Dalton law, which is a really neat idea. It basically says each component gas in an ideal mixture behaves as if it were completely alone, occupying the entire volume at the mixture temperature.
Ah, so it doesn't even see the other gases.
So in terms of its own energy and enthalpy, essentially yes, for ideal gases, it simplifies the analysis tremendously.
That sounds almost too easy. Is there a catch? A place we need to be careful.
There is, and it's a really important one, especially when dealing with entropy.
Well,
When you calculate the entropy or the change in entropy for an individual ideal gas within a mixture, you absolutely must use the partial pressure of that component in your calculations.
not the total pressure of the whole mixture.
No, not the total pressure. You have to use the pressure that specific gas contributes. It's partial pressure, YPM. It's a subtle point, but forgetting it leads to wrong answers for entropy changes during processes. Critical detail.
Okay, got it. Partial pressure for entropy. Let's bring this down to earth again. How does this play out in, say, an industrial process? Like cooling air.
Great example. Let's take air, roughly 79% nitrogen, 21% oxygen by mole. And imagine we need to cool it from, say, 220 Kelvin down to 160 Kelvin. Pretty cold. And let's say this happens at a constant high pressure, maybe 10 megapascals. This is definitely getting into the territory where ideal gas assumptions might be shaky.
Right, high pressure, low temperature.
So if we calculate the heat transfer required using the ideal gas approximation, we might find it's, say, 1,744 kilojoules per kilomole of air.
Okay.
But If we use a more accurate method for real gases, like K's rule, the calculated heat transfer jumps to 3513 kilojoules/kilomole. And if we use Amagat's law with enthalpy data based on compressibility factors, we get even higher, around 3717 kilojoules/mole.
Wait a minute. You're saying the real energy needed is more than double what the ideal gas calculation tells us?
Yes, more than double.
Wow, that's not a small error. That's a massive difference.
It absolutely is. And it really highlights why understanding real gas behavior using tools like K's rule or Amagat's law is so critical. If you design your cooling system based on that ideal gas number, it's going to be wildly undersized. You'll waste energy, maybe the process won't even work correctly, could even be unsafe.
That really drives the point home.
Yeah.
Okay, this next part, you hinted at something deeper, more thought-provoking. We know things mix naturally, right? Sugar and coffee, air. It just happens. Seems simple. But is there a hidden cost? Maybe even a benefit we don't see?
That's a fantastic question, and it leads to some profound thermodynamic insights. Yes, it's common experience. Put two things together that can mix, and they will mix, spontaneously. But thermodynamically, this mixing is a fundamentally irreversible process.
Irreversible meaning?
Yeah.
It won't unmix on its own.
Exactly. Think about it. Nitrogen and oxygen mix easily to form air. But have you ever seen a room full of air just spontaneously separate back into pockets of pure nitrogen and pure oxygen?
No. Definitely not.
Right, it doesn't happen. Because mixing increases disorder, increases entropy. And because it's irreversible, it carries this deep implication. It means there's a waste of work potential. Something useful is being lost. We can analyze this using concepts like chemical potential, partial molar properties. For what we call an ideal solution, this includes ideal gas mixtures, but also things like very dilute liquid solutions. For those, something interesting happens. The change in volume and the change in enthalpy during mixing is actually zero.
So mix two ideal gases, the total volume is just the sum, and no heat is released or absorbed.
Correct. No volume change beyond simple addition, no heat effect.
But you said work potential is wasted. If there's no energy change, where does the waste come from?
It comes from the entropy of mixing. Even if enthalpy and volume don't change overall, the entropy always increases when you mix different substances, assuming it happens adiabatically without external heat. That increase in entropy represents the irreversibility. It signifies that potential to do useful work has been dissipated, lost to the surroundings effectively.
Okay,
Yeah.
So follow me here. When a huge river full of fresh water flows into the salty ocean,
Yeah.
that mixing process, there's actually a hidden work opportunity there that we're just letting dissipate.
Precisely. That's exactly it. The exergy destroyed exergy is basically the useful work potential during that natural mixing represents the maximum amount of work we could have extracted if we somehow made that mixing process happen reversibly. And conversely, it also represents the absolute minimum amount of work we'd need to put in to separate them again, to get the fresh water back out of the salt water.
Which brings us to desalination, making fresh water from seawater. That's a perfect example, isn't it? We have to put energy in.
It's the textbook application, really. You're fighting against that natural tendency to mix. You're reversing an irreversible process, which always requires work input. For instance, calculations show to get just 1 kilogram of pure fresh water out of a large body of typical seawater, the theoretical minimum work you need to put in is about 1.50 kilojoules.
1.5 kilojoules per kilogram of fresh water.
Okay. And that minimum work isn't just an abstract number. It translates directly into real physical things like osmotic pressure. That's the minimum pressure you'd need to apply to the seawater side of a membrane to force pure water through. For typical seawater, it's around 1,540 kPa. Or you could think of it as osmotic rise.
Like how high you'd have to lift the seawater.
Yeah. To naturally separate, you'd need to lift the seawater column about 153 meters higher than the freshwater level. That height difference creates the pressure needed.
Wow. 153 meters. That's really high. We have a significant energy potential locked up in that salt concentration difference.
We absolutely are. And it leads to this really striking final calculation. Consider a major river maybe flowing at 100,000 cubic meters per second. That's a lot of water.
It's a huge amount, yeah.
If you could somehow harness the energy released as that massive amount of fresh water mixes reversibly with the ocean, maybe using hypothetical, perfect, semi-permeable membranes, the amount of power you could theoretically generate is just staggering. The calculation comes out to 150,000 megawatts.
150,000 megawatts just from one big river mixing with the sea. That's like the output of 150 large nuclear power plants, isn't it?
Roughly, yes. It's an enormous amount of power, just
Yeah.
constantly being dissipated naturally, irreversibly, all around the world where rivers meet oceans.
That's incredible. It just vanishes into the environment.
It does, and it powerfully underscores just how much energy is involved in these seemingly simple mixing processes and how much potential work is lost due to irreversibility in nature. It's a vast, essentially untapped energy source.
Wow. You've really taken us on a journey here. We started with, the basics. How do you even describe a gas mixture? We navigated through the tricky bits, the real-world behavior where ideal rules break down. And we ended up here looking at a river meeting the sea, not just as scenery, but as this massive, untapped energy opportunity.
And understanding these principles is just so vital, from the basic composition rules to the complexities of real gases at high pressure, and then these thermodynamic implications of mixing and separation. It's this knowledge that allows engineers, scientists to design more efficient systems, to optimize processes, and really to get a much deeper grasp on our planet's energy balance. It matters.
So what does this all mean for you, listening right now? You've seen how something that sounds simple, gases mixing, actually hides layers of complexity and even this huge energy potential. This deep dive really makes you think, doesn't it? If we can find that much untapped energy just sitting there, where fresh water meets salt water, what other natural processes are happening all around us every single day? Processes quietly dissipating enormous amounts of energy that maybe, just maybe, we could learn to harness one day. What other free mixing or other seemingly simple natural events are actually costing us potential work right under our noses? Something to ponder.